Hi, we are Team Milford 8823C, and this is our prototype for Vex Turning-Point. Now, this is a prototype for the flipper, not for the ball shooter, and what it does is it picks it up, brings it up, picks it up, brings it up, and then puts it on the post. So if you see here, this is how it begins. We'll have the flipper flipping out instead of around, and now we'll be able to control it like you would. Right now we do not have potentiometers on. That'll be a quick addition. Now as you can see, this lift moves just high enough to get to the, we'll work on that too. On the 34-inch post, obviously goes to the next areas too. We're working on our wire management, of course. And our wheels is a 4-wheel drive, a motor on each wheel. And this side has chains for their wheels because we're trying to keep them out of the way for the shooter, which we will be adding in later. Now, here's some more information on the arm.
So here we got an arm, reverse 4-bar, and I don't know if you can see this, but right here we have two sides on this on right here, and right here we only have one. That's just mainly to keep it light, and we kind of got that idea from a Singapore team. And this way we only have to use 2 motors and not as aggressive of a gear ratio to lift it up. So we can manage to lift the entire arm with only with only 2 gears, or not 2 gears, 2 motors. And now to Caleb or Nathaniel.
How many hours have you guys worked so far?
Well, we worked out
71.
for 71 hours. That's the short answer. 71 hours. We've worked on and off. We worked a lot in the public library near our school. We worked rented a room, and we used that to work together. It was a quick spot, centralized, where all of us can meet pretty easily. And then we did take the robot to my house, the lead builder, and I built on it some. But of course, I saved most of it for when everyone could come to my house, and we could work on it together. And this is our end result from the summer's work.
What was the most challenging thing that you created and to overcome?
The most challenging thing probably would be not the flipper, not the base, but the arm, trying to keep it as condensed as possible. Last year, for Vex in the zone, don't worry about that. For Vex in the zone, we had a very large reverse 4-bar. And this 4-bar spanned the entire robot, and our lift for the base, which was another component, there was bases and cones. And the base lift was right under here, right under the lift. This year, we're aiming for a different approach, where the lift is on one side, and the shooter for the balls this year is on the other side. And that was a little different, but also seems to have worked out very well. All that's needed is to work on a shooter, which we're checking with our other teams to see what they have done. Now here's Nathaniel on a little bit about the programming and what we've done.
So, since this is the start of our season, there isn't too much to programming. Right now it basically just drives and flips the claw. However, we have our simple controls are on 1 stick for movement and 2 buttons for flipping the claw. Well, the flipper. And I don't remember the controls.
Well, that's just about it for our robot, Milford Robotics, Milford, Ohio, robot 8823C. We're looking forward to competing in the arena and to see what everyone else has.
Alright, hi there, we're Team 8823D, and this is our robot that we built this summer. My name's Jacob, and they're going to talk about other stuff now.
My name is Nathan, and we have built this 4-bar. We have used a 7-to-1 gear ratio just to make sure we have enough torque. We had 4 motors, because last year we had some burnout problems. And we also have this flipper that we used, and actually we have standoffs here just to make it so it perfectly lines up. And we have worked on it and gotten it to stay in while it flips, which is a big accomplishment.
Hi, my name's Ryan, and this base took a while to complete. One of the main objectives of this to score the most amount of points is to get on a high platform. So we have specifically designed these wheels to stick out in front of the robot. to make sure that we can get onto that high platform.
My name is Colton, and for the program, we used a standard X-Drive program, so the robot can move sideways, forwards, backwards, and diagonally with just rolling the joystick. For the lift, we were planning to add proportional control, but we don't have that yet. For the flipper, we just rotate it.
All right, and this here is our engineering notebook, so the beginnings of it. And in it, we have a notepad, so this is where we take our notes during the meeting each day, and then we put that into our actual notebook. And then in our notebook as well, when we got started, we added a game overview, team roles breakdown, our design brief, and then different prototypes, and it just goes through the design process and really just goes through how our team has developed this robot.
All right, I'm Ethan, and what's coming up next, hopefully, is we're going to try to make a ball shooter, either a linear puncher, a flywheel, or some type of catapult thing to hit the flag.
How many hours have you guys worked on this so far?
87 and a half.
What was the most difficult part of it?
I would say probably trying to get the cap to stay in when we're flipping, because often when we went up, it would, and we started to flip, it would just fall right out, and that would ruin the whole point of the flipper.
Hi, our team is Team 8823B, and this is our prototype robot. As you can see, some parts aren't really fully attached yet. We're getting around that and figuring out where to put what piece at. Basically, each of us had our own part in building this robot. My main part, as of now, was building our cap lift, and basically what it does is it can grab a cap, and then it'll spin it so it can be of our corresponding color. So say we're blue and we're pick up a red cone, we can flip it around so it's a blue cone instead. And that was basically my part.
Okay. This is a ball shooter, which is called a linear puncher because it can punch things using a stupid amount of force. It kind of skips when it reaches the end of it like that. It's supposed to suddenly push forward and kick it out of the where it's supposed to be and launch it maybe five or 6 feet.
Yeah, and I designed this ball lifter right here, and it goes connected up to the wheels right here. So as we drive sideways with these wheels, which I'll show you, these wheels allow us to drive sideways, forward, back, all the other directions. And so as we drive sideways, it will go and pick up the ball, and that will lift the ball. So if I rotate this wheel right here to pretend like we're driving, it will lift the ball up this right here, and then it will put it onto the loading area, which would put it onto the launcher right there. So don't launch. You can go.
So our base, we have a 17.5 by 17.5 inch base with mechanism wheels that help us go side to side while allowing us to go front to back. Our ball lifter here is connected to the back wheels, so every time we go forward, the standoffs here go up, and then we'll probably put our 6-bar here or somewhere here after we redesign this.
We're also thinking about doing like a half and half design where the ball shooter is on this half, or the and the cap lifter and flipper is on this side. That's just one of our options that we're thinking of. Awesome. Yeah.
So for our lift design, we had a couple of concepts, like maybe a linear or lift or a maybe a 4-bar, a reverse 4-bar. But ultimately, we decided on a 6-bar, which, as you can see, is here, albeit partially completed. The idea was that the 6-bar would allow us to reach a little bit farther and put the in comparison to a 4-bar and put the caps onto the poles.
Alright, so I'm mainly doing, at least planning our programming side of things. We haven't really started on any programs yet, mainly due to the fact that we don't really have a computer to do that. But, yeah. Well, anyway, so we're going to have to program how to get it side by side. We're going to have this, how far it goes back. For this, we're going to have to program, we're going to have a potentiometer that limits the amount it goes. And we have physical stops here so that when we first put on the potentiometer, at least, it doesn't break.
So throughout most of the summer, we've actually come up with a lot more ideas than what you see here. At first, like our first robot we built was basically a catapult, where it was a base and it had a catapult to shoot the ball, and we decided to scrap it mainly because it was really, really bad and it didn't shoot that far. So we took that apart, and then later on we built our lift and our cap to like test it out, see how well it worked, and then right now, yeah, and like made our own custom slides, and then now we decided to mount our shooter on to see like how much space it'll occupy. We're probably gonna like squish this in and like make it more simpler so it doesn't take up enough space in order to go with our half and half plan. But that's basically all the progress we've made as of now. There's gonna be a lot more though.
Yeah, so thanks for watching our description of our robot.
How many hours have you guys spent on this?
We have spent 88.5 hours, 21 builds, I believe.
No, like 31.
Oh, 31.
What was the most difficult part that you had to work on?
The shooter.
Definitely.
Things from breaking.
Yeah, that and definitely the shooter, because it would, for some reason, most of the time malfunction, and we would never figure out why until like a day later, and then we would have to like redesign it and all that until eventually.
Maybe 5 feet on a good day.
Yeah.
I mean, if it rolls, it could get 12 feet.
It's a so-so
Also,
reliability.
It has a lot of force because it dents this ball.
And this is a hard shell ball, by the way.
It's not soft.
It's not foam.
So
Yeah.
Way too overpowered for what
Yeah.
it's meant
Right.
for.
Well, bye. That was our robot.
Yeah.
Thank you for having us. Bye.
Oh. Good afternoon, everyone. This is Team 8823E, and I'm Kylie.
I'm Monica.
I'm Emily.
I'm Sierra. I'm Clara.
Okay. And this is our robot that we have made. We spent about 60 hours on building this, but not just this. We made tons of different other prototypes and everything. This is just what we have so far. Okay, so let's start with the cat flipper. We don't have a cat right now, do we? No. But we...
Oh, they have a cat.
Yes, go get it, Clara.
The cat flipper.
Okay, so this is our cat flipper, and there are like notches in this cap, so that's why these standoffs are here to get into the grooves. And then it lines up here, and then with enough force, it would, I don't want to knock it off the table, it would just flip over the cap. And we're probably going to add a potentiometer on it so it doesn't hit this. So that's the cat flipper. Okay, now we can talk about the prototype catapult.
So we have a prototype catapult where it's not exactly finished because it can't reload itself, but if you push this down and then put it like that, it reloads it, and then so the gear would spin and it flips and it would just snap and throw the ball.
You slapped the mic. Sorry.
Okay. So, what we have right now as our temporary catapult is this. And the idea is it would drive up to a ball, pick it up, and then throw it with enough force.
Oh. And also another part of the competition is recording everything that we've done. So I've done the notebook and we've logged every failed attempt and every good attempt at doing these tasks of flipping caps and shooting balls.
Yep.
So
Did you should I just say like what we don't know?
You can say like talk about the base and stuff, yeah.
Currently, we don't have a lift because our main focus was for the cap flipper and the shooter, and also for our base, this is just basically to hold everything together, and I'm pretty sure that we're gonna have a higher base for the getting onto the landings.
Yeah, the PVC pipes,
Mhm.
getting over those.
How many hours have you worked so far?
I already said like about 60 hours.
A little over 60.
What was the most difficult part so far?
I hated the prototype flywheel.
Yeah.
That was difficult.
Prototype flywheel is kind of aggressive.
Oh yeah. I think the catapult to me. I think
yeah, that
because
too.
we're still working on it, and we've been trying this for every meeting we had. We've been talking about like making a perfect catapult, and I mean we're still not there, but that's why I think it's more difficult. But
We will get there eventually.
Yep.
Bye.
Bye.
Okay, so we're team 8823A. My name's Shreya.
I'm Sam.
And I'm Catherine. Okay, and this is a robot. So this is our lift. It's a reverse 4-bar. And so it has a flip down claw, so when you raise it, the claw just flips down. And it also turns in caps, and it can score the caps on the lower poles and the higher poles.
Our wheels are lowered underneath the base so that we can drive up onto the platforms. They have this little bit of C-channel underneath the base, and then there's a bearing underneath even that. So the wheels are very low.
Okay, and then our catapult uses a slip gear. So we have our gear ratio to just a normal gear, and then it goes over to the slip gear to fire it with rubber bands. And then we also have a ratchet, so that as we move the catapult down, all the stress goes onto the ratchet instead of the motor, so it can just hold there in our down position until we move the motor more, and then it fires.
How many hours have you put in so far?
58.
What was the most difficult part?
The lift.
Why was that?
I've never built a lift, a double reverse 4-bar, so, and getting the spacing because we had to make it really narrow in order to fit the lift and the catapult on the robot. That's why.
Okay. What's the next part you're going to work on?
Our catapult, we need to fix the angle so that it fires.
Yeah, and we need to
its flags.
fit it in limits.
Yeah, it needs to be a little bit smaller. Catapult.
Where is it going?
I'm gonna fire it at our workbench. You're gonna just fire it that way. It's not that great. Okay, ready? Are you ready?
Oh, impressive. I like it.
Thank you. Yeah.
Do it again.
Okay, ready?